Okay, we will start the third presentation for today. This will be done by Mike Turquette, kernel hacker, who will tell us how to work correctly with power management. You're welcome. You're welcome.
Thanks, everybody. So I gave a presentation yesterday, but for those of you that didn't attend that, I'll just give a quick background. My name's Mike Turquette. I'm CEO of BayLibre. I worked at TI, Linaro, San Francisco startup doing some cool devices. I wrote the Common Clock framework, and I maintain it today. And as I was working on these slides, which I maybe finished about 5 minutes ago, there's a ton of slides in only 40 minutes. So I'm basically going to go through this stuff pretty fast. And but I don't want that to discourage you. If you have a question or a comment or a disagreement, please raise your hand at any time and just interrupt. Yeah, there's 51 slides, and there's a lot going on here. So I'm an ARM and MIPS SoC hacker, so that's my focus. The concepts in this presentation apply to really all modern system-on-chip designs, but some of the terminology I use is specific to the ARM ecosystem. And this presentation is actually the evolution of training that I made 6 years ago when I was working at Texas Instruments. So a lot of things have changed and a lot of things have stayed the same in that time. It'll cover basically the most basic aspects of the physics behind power management, a little bit of electronics background, like how the hardware actually works, how we save power, and then transition over to the Linux and the software aspect of it. You know, what are the interfaces you need to be using to try to save power in your device drivers? And also, you know, we'll talk a little bit about the ways in which Linux lacks the expressiveness to properly do everything that these chips are capable of, which I think is a fairly interesting topic as well. I don't think we'll get through everything, so the slides will be shared afterwards, and there's also links in here to other presentations that go into like lots of detail about specific subsystems. I encourage you to go through and look at those afterwards. So let's dive into the fundamentals of power management. You know, we'll start with like a high-level overview, and then we'll dive into Linux later on. So basically, like, what is power management? It's a strategy to try to save power, ideally without impacting performance, right? So where there's you know, some opportunistic way to save power without ruining the use case or ruining the user experience, that's what we want to do. You can use power management to invasively impact performance, and you might need to do that in certain scenarios where you have like thermal runaway issues or current limitations and things like that, which we won't talk about. Those are sort of outside the scope of this presentation. You know, why do we care about saving power? So these are in no particular order, but my perspective has been mostly on battery life, prolonging that, and having mobile devices that are running off of a lithium-ion battery. But as well, you care about it for a lot of other reasons, including the environment. And all of these topics up here are under discussion today on the Linux kernel mailing list and on the Linux PM mailing list. You see people working in the data center, people working for all kinds of different devices, and they care about all of those issues. So raise your hand if you've seen this before. This is like super advanced stuff. Okay, 1 or 2 PhDs in here, that's good. So power, it's an instantaneous value. It's the product of voltage and current, right? And if I got that wrong, I'm super sorry. So anything to the right of the equal sign, if it's 0, then the whole thing is 0, right? That's how math works. And you know, lower power is a good thing. If we can save power without you know, damaging or hurting the use case, then that's what we want to do. Energy is an important concept which is distinct from power. Energy is a summation of power over time. And this is especially useful when energy is a finite resource. So when you're plugged into a wall, I guess it's like, you know, it's technically finite, but you know, we think of it as infinite amounts of energy. When you're on a battery, you have a finite battery capacity. So energy is like a distinct concept, which is also very important. Okay, so we've just mastered physics, right? We're all PhDs now, we've got it. Now let's kind of move on to the electronics aspect, an overview of how the hardware works and how it's made. So let's start with sort of the modules that are within hardware. So modules are the IP blocks or the functional blocks that are inside of a chip or a system on chip. And they can be, you know, a CPU or a DSP, they can be a GPU, it could be I/O controllers, it could be serial I/O, you know, storage controllers, it could be a ton of different stuff, network devices, etc. A module is just an IP block, right? It does something functional. And they're typically composed of logic and memory inside, and we kind of manage those a little bit distinctly when it comes to power. Modules can be in an active running state, and they can where work is performed, and they can also be in an idle state where no work is performed at all. And there might be multiples of either of these states in either case, which we have policies and governors to control which state we're targeting. So every type of power-saving technique can really be put in one of two buckets or two categories. You have active power-saving techniques, which is ways to save power while you're doing work, while you're running. And then you have power-saving techniques while you're not doing work, while you're idle. And this is like basically the dichotomy for the whole power management universe. The most basic and obvious type of saving power is to turn something off. Like you're idle, you're not doing it, just turn it off. Well-written Linux device drivers will aggressively turn off resources when they're not using them. But I mean, most of them are not well written. There's a lot of, sort of crappy or basic drivers. One thing you see quite often is that in a module probe, it'll enable the power resources that it needs and it won't disable them until module exit. Or what's even more common than that is that there's a lot of device drivers that are totally power unaware. They have no clue about power. They rely on the bootloader or the firmware to set up the clocks, the regulators, and all of that stuff. And they never even consider trying to manage power themselves. So maybe someday we can change this. On the active side, these power savings are generally performance related, right? So we want to scale performance for the use case, for the needs that we have at the time. And if we can get away with a lower performance, that's good. It means we'll save some power. And we want to do it in such a way that it doesn't damage the use case that we're trying to achieve. Linux doesn't actually have a device performance framework today, like a generic device performance framework. We'll get into that later on. But it's worth noting that a lot of vendor trees, downstream vendor trees from companies like Texas Instruments and NVIDIA and Qualcomm and all these guys, they all implement something like this, some kind of generic device performance framework out of tree. And it's a major problem that I think I would like to solve, and if there's interest in the room, then we can just go after here and solve it real quick. So. For extremely performance-sensitive applications like 3D gaming or stuff like that, aggressive power management may not be much of an option, unfortunately. It may impact the use case or the user experience so much that you see a lot of times where applications or device drivers will just turn off power management for those use cases. So that kind of sucks, but it's the reality. All right, so this is our first look at an actual power management policy. I'll use my laser pointer. So on the, oops, turn it around. So on the left, we have kind of like what I call a race to idle philosophy. So the idea is to run as fast as possible and get the work done very quickly and spend more time in a deep idle state. On the right side of the screen, we have a different power management policy, which is to run slow. Now, the duration of the runtime is increased, but according to these made-up charts, this actually saves a little bit of power. This strategy is used very commonly in Intel and ACPI type designs, where they have a very fast wake up from idle and a very good power savings in idle. And this kind of strategy is used very often in the ARM and the MIPS ecosystems. There's not one that's better than the other. And I see people kind of debate, race to idle versus running slow. It just depends on the use case, the architecture of the hardware, and then sort of what the workload is like. For instance, imagine the difference in software workload between a device with a touchscreen and the user occasionally touches it and there's some bursty performance that you need versus a data center with a server having the type of MapReduce workload or something like that. They're totally different. Yes? Yeah, sure. So, okay, this gets back to the fact that energy is sort of the summation of power over time, right? So, in this case, for this particular hardware, the total amount of power that we draw over 4 seconds that's necessary to complete the task, you add it up, and it's less than the total power that we drew for all 4 seconds over here, and that's just a function of the different type of hardware, right? Yeah. So in fact, these boxes where they give some fake numbers are maybe I should remove those because it's more illustrative just to show the two different policies. I'm not trying at all to imply that this version will always save power over this version because that's not true. It just depends on the hardware. Okay, so now we know about active and idle power savings, and we've talked a little bit about policy. So now let's talk about how we interact with them. What are the knobs that we have control over, from software? And the two major knobs that we have control over, you can think of them as basically being voltage and current, which is the right side of that P equal IV equation. So the important thing to consider about voltage is that the way we think about it in software is that it's a slider value, right? We can, we have lower voltage, we can have higher voltage, and we have a range, a continuous range in between that we can change. So for active power savings, we slide this value when we want to run fast and have high performance, where we have to increase clock frequency and we have to increase voltage at the same time at the high end. If we want to save a little power and try to run slower because we don't need that performance, we scale voltage down along with clock frequency. For the idle power savings, we can also scale voltage because let's say you have a little bit of a memory inside of a module that's retaining some state, but you're idle, you're not doing work. You may be able to lower voltage a whole lot, like down very, very, very low, and retain that memory using some low power retention magic in the hardware. And so in this way, imagine voltage as a slider, and we can go up or down and depending on the type of power saving technique that we're using. On the other hand, current is more of an on or off affair. We tend to think of this as clock gating or power clamping, power island, which we'll get into here shortly. And this is really a binary sort of on or off thing. And these are the two main knobs that we have. We can sort of scale voltage or we can power clamp stuff. And that's the fundamental sort of knobs that we have to play with from software in order to actually save power. Okay, so welcome to acronym hell. This is an incomplete list of some of the ways that and interfaces that we have to try to control power management hardware. So if you check out the mailing list for ARM and MIPS SoCs, you might see a lot of acronyms like PRCM, PRCMU, CAR. These are typically like Power Resource Clock Manager. This one is nice. It's Power Resource Clock Manager Unit, which is a big difference. CAR, I think, is clock and reset controller. Yeah, I think I just made that one up. I don't even know what CRM is. But anyways, they all kind of do the same thing, right? There are some memory mapped registers that you touch, and they control regulators, they control clocks, they control resets, they control power related stuff. Adaptive voltage scaling. There's also firmware interfaces. For a long time, this was mostly, you saw this in the Intel world with ACPI. Where all the power resources you have to go through ACPI. We're seeing a lot more adoption of that in the embedded ecosystem as well now. ARM released the PSCI, which really was originally only targeting CPU power management, but now SCPI was doing CPU performance management, and now SCMI is supposed to do the whole platform, all the different peripheral devices, all the other stuff, GPUs and all of that. Texas Instruments released some patches for the SCI. I don't even remember what that stands for, System Control Interface or something. And so firmware interfaces are starting, I think, to take over the world a little bit. There's also bespoke communication with power management ICs. A lot of times they're wired up to an application processor or I2C, and there's some message passing back and forth to control the power state of the chip. Okay, so we're about a third of the way through the material. If the person next to you is asleep, just nudge them. We're getting into the good stuff now. Are there any questions I can answer so far? Anyone have a question? I hope it's not too fast. I'm like super worried that we're not going to get through all the material.
Because we have a coffee break next. We can add at least 5 minutes for you.
Okay, I don't want to get in the way of coffee though. Oh yes, we do have a question.
Okay.
Okay. Hey again. Actually, not a question, just a remark that many driver developers, even nowadays, totally forgot about power management.
Yes.
And that is really pity.
Yeah. That's why I'm here. We're gonna solve that problem. We started by giving everyone a PhD in physics, and then a PhD in electrical engineering, and by the end of it, we'll have a PhD in Linux power management. So. Yes, but I agree fully with your point. Okay, so let's kind of put all of this together, and first we'll do a review. So we know that scaling voltage or cutting current are ways we have of saving power, at the physical level. We know that modern SoCs have lots of individual blocks of hardware, and many times these can be power managed independently. It's not like the whole chip is one big monolithic thing. We can do fine-grained power measurement within the chip. We know that different types of power saving schemes and policies are necessary for different types of hardware, different types of software workloads and use cases. And we're all experts now, right? So let's talk about real hardware. So modern SoCs, I mentioned before, they're filled with modules or IP blocks. These can be a variety of different types of things, crypto accelerator, CPU, whatever. The thing that for me makes SoCs very interesting to work on is I'm a fan of computer, architecture, hardware architecture, and SoCs are all very different. They're super messy. A bunch of different IP blocks are glued together. They have clock trees. They have power supplies. There's a DMA between devices. You have a variety of interconnects, shared memory, interrupts, mailbox schemes, and every vendor does it differently. There's not a standard way to wire up a platform, and so that kind of keeps things interesting. And the way that we have to that presents some challenges to us when we want to create like one nice subsystem in Linux that manages all these different components, because underneath the hood the hardware is very, very different from manufacturer to manufacturer. So for modules, which is sort of the lowest level component that we're going to talk about, they basically require two things in order to operate. They need to have power supplied to them, and they need to be clocked. In this example, we have module X, which is like everyone knows what module X does. It's self-explanatory. And it has two clocks, the interface clock and the functional clock. Gating either of these clocks will obviously impact the functionality of the module. It may turn the module off, or it may only turn off a part of the module. But it will also save power. And clock gating is one of the most fundamental things that we have in terms of trying to do some basic power savings. A lot of times in chips, in fact, if the only thing you do is enable clock gating for the whole platform, that's where you'll get like 80% of your power savings. That's sort of the 80-20 Pareto principle. And so this is the lowest level thing that we can do, just do clock gating on modules when we don't need them to be functional. So kind of the next level up, and there's no good standard terminology for this, but I'm calling these idle domains. A lot of times you hear about power domains, power areas, and what are these? These are basically areas on the chip where we have electrically isolated transistors, and you can imagine a power or an idle domain as being a container filled with a bunch of modules that you can idle all of them, and you can lower the voltage or totally cut power to these modules. So, but in the previous slide we talked about clock gating. Now we're really talking about changing the power that we supply to these modules. This is an idle power management thing. So if we lower the voltage or cut power to an idle domain, it's because no work is being done on these modules. They're idle. They're not doing stuff right now. What kind of stuff might you see inside of an idle domain? Well, sometimes, let's say a common pattern I see is a GPU module might have its own idle domain, a GPU domain that wraps around that module. Other times you'll see like a peripheral idle domain or power domain that'll have lots of I/O controllers or other like smaller, more manageable peripheral devices. So lots of modules within a single idle domain. These idle domains, they may just be simple on and off semantics. It's got power or it's totally power clamped. But also you'll see schemes where there's intermediate levels of power savings that you can get. And I mentioned earlier, for instance, like lowering the voltage quite a bit to do a little bit of memory retention is a common one that you'll see. So the reason you want to do this is because if you save, if you retain context in the memory of these modules, then you can resume work very quickly. The latency, the amount of time it takes you to come back to an active running state is very, very fast. Whereas if you totally power gate them and you lose all context in memory, then you may have to either reinitialize the hardware in the Linux device driver, which takes some time, or you may need to copy some saved context out of DDR back into the memory. So that's why all of these crazy hardware engineers have come up with these schemes. It's all about just trying to optimize every little aspect of it, optimize the right amount of power or optimize the right amount of performance and wake up latency that you want coming out of idle. All right, so here's our first real-world example of an actual chip. This is the AM335X. If you guys are familiar with the BeagleBone Black, which is a fairly well-known development board, this is the application processor on that device. And so here we've got an actual block diagram of how it really works. You can see up here, this is what I mentioned earlier. This is a power domain or an idle domain just for the GPU. This is for doing graphics and 3D graphics. And it's a whole power domain dedicated just to that one GPU module. Similarly, we have another power domain which is dedicated just for the ARM CPU, the Cortex A8. Then over here we have this big giant peripheral power domain. And it contains a whole bunch of modules. A lot of them will be I/O controllers or multimedia accelerators, things like that. Interestingly, the bottom kind of half or third of this slide, this is a Cortex M3 microcontroller, and this is actually, its only purpose in life is to manage all the power bits. This thing is what actually controls all the power states, both idle and active, for the whole SoC. And there's a custom message passing protocol that TI devised between Linux and the Cortex M3 microcontroller. So that's one way of doing it, sort of the firmware interface that I discussed earlier. Interestingly also, this chip is, it really only does mostly idle power savings. It has very little capability to do active power savings where you scale performance up and down. Basically, you can turn things off and turn things off in different levels of off, but performance is mostly fixed with the exception of the CPU, which the CPU can scale performance a little bit. All right, we're almost done with our electronics overview. So performance domains are analogous to the idle domains we just discussed, right? It's electrically isolated transistors. They're going to typically be fed by a dedicated SMPS or regulator. And what they do is you can scale voltage. Remember before we talked about scaling voltage on a slider, right? High voltage, low voltage, as a function of performance. And so that's what these can do. In this particular example, we actually have an idle domain, the green box, which is nested inside of this bigger performance domain. And this is a common pattern that you'll see. And so, for instance, a performance domain, the most obvious example that I can give you would be a CPU, right? You have a dedicated regulator that feeds into the CPU, and if you want your CPU to run fast, you change the clock and you also scale voltage up. If you want the CPU to run slow, voltage down and clock goes lower, not in that order. But this is like a super complex diagram to explain some simple stuff. All right, and so here's our final real-life hardware example. So I used a different chip, OMAP 3, and this was the chip that was used in the Palm Pre, the Droid and the Droid X from Motorola, the Nokia N900, and that was in the good old days back when there were multiple Linux-based distributions for smartphones. Now there's only one. Sorry to any Mozilla employees in the room. So. The smallest white boxes here, these are basically the modules we've been discussing. So like IVA is actually a video, it's actually a video accelerator block. The MPU is the CPU. SGX is the Imagination Technologies GPU for doing 3D stuff. So these are the actual functional modules. The dashed lines are the idle domains or the power domains that can clamp power in idle things. And then these big colored rectangles are the voltage domains or the performance domains where we're actually scaling performance for all these modules up and down. So you can see that a lot of times things get grouped together. Like we have this one giant voltage domain that includes, it's basically the ARM and the CPU performance as well as some of the multimedia accelerator performance for doing video acceleration, video decoding, video encoding, things like that. And then and some of the other domains are sort of like put together in a logical way. Like you can see the display subsystem is sharing a performance domain with the camera subsystem. Those two things, it kind of makes sense for them to, their use cases will probably have them both running fast at the same time, right, for this particular chip. Okay, so we're now masters of physics, electronics, and modern SoC power management capabilities. So we can now dig into the actual Linux stuff, which is probably what you care about the most. The actual Linux subsystems that we use to control power. But I think it's important to have that background because otherwise, a fundamental question is sort of how does software control power management? How do you do it? It's good to have the background. So let's start with idling. In my opinion, the problem of sort of idle power management is much easier to solve than active power management in general. Turning things on and off is a fairly straightforward thing, but controlling performance is not. So we'll start with idle. Runtime PM, it is the interface to control the power state of the hardware for Linux device drivers. Before drivers do any work, they should call PM runtime get. And then when they're done doing work that involves the hardware, they should call PM runtime put. These two functions basically define a critical section in which we expect the power resources to be enabled. After you call PM runtime put, it's possible that the device will acquiesce and hit a low power state. Of course, other device drivers may be using the same device, so you don't really know when it's going to happen. But the point is that that's the critical section of work. Lazy developers might just call PM runtime get during module probe and maybe PM runtime put during module exit, and those people are not my friends. So, but on the other hand, I also sympathize with developers who maybe they don't have access to the datasheet or like a really deep understanding of the hardware, right? They may not feel comfortable trying to aggressively define very small sections of critical work. But yeah, I mean, too bad for them. So. Oh, and one final interesting thing is that in practice, everyone, when they speak about the subsystem, they say runtime PM, but all of the functions begin with PM underscore runtime. So when I'm grepping, I'm always mixing it up and getting it wrong. So, okay, so GenPD is sort of adjacent to runtime PM. Generic power domain, it manages the power management hardware for groups of devices. And so this is it's a subsystem that actually you plug in sort of your power management provider drivers into this subsystem. And it means that a GenPD driver for an Intel platform, let's say, might talk to a CPI, or for maybe a more basic ARM platform, it might manage directly clocks and regulators within the driver. But this is the actual Linux device driver that talks to the PM hardware. And then all the different client drivers that use that PM hardware, they attach to this generic power domain. And again, this is just for idle. This is just for turning things on and off. The end result is that when you call PM runtime get from, let's say, your MMC controller driver, it'll go through the PM runtime code, which will then go into the generic power domain code or generic PM domain code, and it will say, oh, okay, for this particular device, you're attached to this regulator and this clock. I need to enable those before you continue doing work, before you write to the SD card, before you read from the SD card. That's the end result of all this abstraction and layering of code. These are the relevant headers and documentation. So if you're not familiar with these before, you know, pmdomain.h, pmruntime.h, and there's some good documentation out there. As well, there's a nice device tree binding for defining power domains, which is very important because I mentioned before that you have to attach a power domain to all the different devices that use it. And in the ARM world, device tree is the way we create linkage between devices. Okay, so Runtime PM and GenPD, they're pretty detailed APIs and subsystems. There are many great presentations out there already. I just don't have time to go into deep detail on them. But here are some links. Most of them are, yeah, these are all from elinux.org. And these are all great presentations. I definitely recommend that you check them out. Okay, so now we'll talk about CPU idle. CPU idle, it's the subsystem in Linux for idling the CPU. And it's an opportunistic idling mechanism, right? The idea is that it doesn't want to affect the scheduler. The idea is that the scheduler is scheduling work, and if there's some idle time between when the last task finished and when the next one's going to be scheduled further down the line, then you can opportunistically try to sleep during that time and save some power. You don't really want to impact performance if at all possible. And also, it's also quite difficult to estimate when that next period of work is, because the scheduler knows when it needs to do the next bit of scheduled work, but you may have interrupts that just kind of show up asynchronously and wake up the CPU. So we have some heuristics in the governors that try to estimate, based on historical data, when the next interrupt will come in. It's a pretty hard problem to solve, and it makes for some interesting code. Okay, so for those of you that are not asleep, you may be thinking, well, we already have a mechanism for managing power for devices, Runtime PM and GenPD. Why are CPUs special? Why do they have their own subsystem? And the answer is actually just that it predates, CPU idle's been around for a long time. It predates Runtime PM and GenPD. And it was written by CPU vendors or distro vendors that were very focused on the CPU and not so much the whole platform. If your company makes CPUs and that's what you do, then that's what you're going to focus on. But it has a bit of overlap, I think, with what Runtime PM and GenPD are trying to do. And so there are ongoing efforts for some time to unify these subsystems. What that will likely look like is that there will be CPU idle drivers that will just use Runtime PM callbacks inside of the driver. That's what it'll do. The Linux Plumbers Conference in 2015, there's a nice little one idle to rule them all. And if you enjoy power management or elves or dwarves, then I recommend that you check out this presentation. Kind of explains the efforts to unify them. All right, and then the next question is, okay, so we now from Linux, we have APIs to turn things on and off when we need them, right? But what about what I mentioned before, where you have different levels of off, right? You're not just fully power gated, but also maybe a little bit of memory retention. What API do you use to control that? And for that, we have per device power management quality of service, which is like a huge mouthful to say. But in short, the most important thing that this interface does, it lets you place a wake-up latency constraint against a struct device in Linux. So if you know that you need this device to become available in a very short number of time, let's say some milliseconds or something, then you can place a constraint against that, and that constraint will go through PMQoS, filter down through the generic power domain subsystem, and for your particular hardware, it'll go into the driver and say, oh, okay, well, for this device, given this constraint, you can't go all the way off and power clamp. Instead, you need to hit like a more shallow idle state so you can come back quickly and satisfy that software constraint. So this is really all about wake-up latency constraints, and PMQoS is how we control that. If you don't have constraints at all, or if the constraints are very forgiving, very slow, then yeah, you can just go into a deeper idle state or turn the whole thing all the way off. All right, these are the headers. This is kind of the primary thing. If you grep for this in the kernel, you'll see several examples of where device drivers are controlling basically the wake-up latency and the idle state of the hardware that they manage. And this goes into effect when PM Runtime Put is called, and basically all of the active usage of the device is done, and the device can acquiesce into an idle state. All right, so yeah, we're making good progress here. So what is system suspend and resume, right? Because system suspend and resume has been around for a long time, and I haven't talked about it yet. So how is it different than Runtime PM? Well, the best example I can give is, Runtime PM is this fine-grained kind of thing where you're trying to save power on all the different modules on the chip, right? I mean, you have device drivers that map usually one-to-one onto these modules inside of the SoC. And suspend and resume is a big hammer. And the best example I can give is the close your laptop lid use case. So, when you close the lid on your laptop and you toss it in your backpack, you really want the device to basically turn off, to hit a low power state and to stop running, right? Otherwise, you're going to waste your battery and potentially your backpack will burst into flames from all of the heat, especially if you have a high performance laptop. So this is different than how CPU idle works. CPU idle is trying to opportunistically save power between periods of inactivity, or within a period of inactivity where no work is being done on the CPU. Suspend actually explicitly tells the Linux kernel scheduler, stop scheduling work. Do not schedule work again until you're woken up by someone opening the laptop lid or pressing the power button or hitting a key, right? So fundamentally, totally different approaches. This is a highly invasive approach. You can look at the struct def PM ops to see how it's used. These are the suspend and resume callbacks that many of you will be familiar with inside of a device driver. Similar to the CPU idle and runtime PM migration, this stuff might merge as well with runtime PM, and that's been an ongoing discussion for some years. Where if you already have code that can put your chip into a low power idle state with runtime PM, can't you just reuse that to implement suspend and resume? And for many platforms, the answer is yes. So we're starting to see a migration where these two subsystems are merging. CPU Freak is similar to CPU idle in that it's CPU specific power management subsystem. It controls the frequency and the performance of a CPU. There's a variety of governors or policies. A lot of these are actually out of tree. So if you guys have been hacking on Android devices, you might be familiar with the interactive governor, which is not merged into the mainline kernel. It's not upstream. And here's the sort of the paths for this stuff. I think this is a super well-known subsystem. I won't spend much time on it. And I think let me see, I think there's only like 4 slides left, so I'll wrap it up real quick. DevFreak is basically a copy-paste of the CPU Freak code from a while ago. It's meant to control performance for devices. But in fact, it's really only good for certain types of devices, like a memory bus, which has a struct device in Linux, or maybe a GPU. Basically, processors or things like that where you have a polling loop and you have a policy, some kind of like smart governor policy. It's only good for those types of devices. I'm not a huge fan of the code, but it's interesting to look at it. You know, if you have performance counters, for instance, for your memory bus, and you can detect that you're over a certain saturation level for your bus, then maybe DevFreak is a good opportunity for you. That's a place where you can receive the interrupt that you get when you hit your saturation limit on the bus and increase performance there, so you're not oversaturated. The OPP library is just a simple data structure for storing tables of common performance information and doing operations on those lists. So an operating point is basically a pair or a tuple of frequency and voltage. This isn't used by Intel and ACPI. Those guys have p-states, but this is used everywhere else where you're using clocks and regulators to manually control the performance. Also, interestingly enough, the thermal frameworks will use this. So for instance, if the device is getting too hot, then the thermal framework might come in and remove the highest operating point from the list for that device, so that you can't your governor or your policy can't select that, and it'll help the device cool down. Okay, so this is actually the last slide that I really wanted to get to. Runtime PM for performance. So we have Runtime PM, which is idling devices, and we have that upstream. A lot of people are using that. It's a great framework. But we don't have the same thing for performance. It doesn't exist. There's no way for an MMC controller that wants to scale performance based on the class of SD card that you plug in there. There's not a good way for it to say, oh, I need to configure the system in such a way that I have higher performance because this is a super fast card versus, oh, this is a crappy class 4 card. I can deal with lower performance, right? And there's no way in Linux to do that. I think this is a huge problem. A lot of different devices have the capability to have different performance levels, and we don't have an expressive API. So one thing that I've been discussing with people is whether we can extend Runtime PM, which is only focused on idle today, to extend the idea of performance to it, to reuse maybe PMQoS is currently doing wake-up latency. Maybe we could add throughput, or maybe we could add sort of a performance level to PMQoS and reuse those APIs and extend them for performance. If you have an interest in this area, then please find me after the talk, and I'd be really happy to talk about it. All right, we didn't get to talk about all these things. That's fine. I already anticipated that we'd run out of time, so I made this slide ahead of time. And I think we have a few minutes left for questions. So these are I just want to thank the wonderful TI for putting all these nice data sheets out there, which I copied images from. And also, you can follow the Linux PM mailing list if you're interested in this topic some more. A lot of good discussion happens there. So.
Actually, thank you, Mike, for this deep presentation, starting from the physics PhD. And now we have 5 minutes for the question in sake of the coffee break.
I have been developing drivers for Linux not for a very long time, and I have never thought of caring much about power management and this kind of stuff. My question is, how much effort does it take to implement these things, and how much profit does it bring? And does it worth it really? Should I care?
Yeah, well, you should definitely care. But the answer to both the questions about how much effort and how much benefit it brings varies a lot. So one of the easiest things that you can do in your driver is just put runtime PM get and put callbacks around the critical sections of work where you know your driver's touching the hardware. That's very simple. It's 2 lines of code for that critical section. That's all you have to do. This is what we call runtime PM adapted drivers. And in general, it would just be really great if people started doing that, because for people like myself that care about runtime PM, in order to test, we have to go and hack up all these drivers and put runtime PM stuff in there. If the driver authors themselves would just do that, I mean, it would take them no time. It doesn't require any extra validation on your part. So for that aspect of it, I think it's quite easy. As far as the amount of benefit that it will bring you, that depends on the platform. If you have kind of a big dumb platform that doesn't have really fine-grained power management capabilities in the hardware, then you'll probably never hit a state where your hardware is able to idle and save some power. But if you're working on a more advanced chip, especially one that's supposed to run on a battery and it has all this magic, then yes, you won't ever achieve a low power state unless you use this stuff. So.
Thank you.
Next question.
Hello, thank you for your speech. I have a question. You told that when you close your laptop, the scheduler sleeps. And could you please tell more what happens when you open your laptop again, and how does it work?
Oh, yeah, so, okay. yeah, if it works at all. So when you open your laptop, I mean, basically, at the hardware level, you have interrupts which are wake-up capable, right? And so the laptop lid will more than likely be wired to a GPIO. That GPIO is wake-up capable, and that will hit the application processor or the power management IC and say, oh, it's time to wake up. But the point is that a lot of those GPIOs or interrupts are not wake-up capable, right? So you as a system designer, you have to make sure that if you only have 16 or 32 or 64 wake-up capable lines, then you have to make sure that you properly assign them to the right stuff. The power button on the side of your phone is another example, right? But think about this. So your Android phone, the screen turns off, it's totally black, it's been black for 10 minutes. The phone is suspended, it's in suspend to RAM. You touch the touchscreen, nothing happens, right? That's, it's not powered, there's no wake up that's happening there, but you hit the button and it does wake up, right? So that's a way to illustrate the different types of events, right? They're two different classes. The ones that wake you up from a deep sleep state, or ones that turn you on from power off, versus the ones that only work when you're active, when you're running. So.
Thank you. Next question.
So my question is about chains of devices which may have dependencies. So think about, for example, Ethernet, MAC, and PHY. So how it is all done in existing PM stuff?
Sure. So as far as the power management dependencies go, you would model those in GenPD, the generic PM domains. And in fact, a PM domain is a struct, and they can be nested inside of other structs. So you can create hierarchy of power dependence that way. There's also a more general problem where there's a lot of resources that device drivers have in Linux that are not properly modeled. We know that they exist in the hardware. There's sequencing. There's functional dependencies that exist, and we don't have a good way to express that in Linux. Rafael Wasaki had about a year ago, he had an RFC on the mailing list trying to find a new way to describe these resources and these interdependencies. And I would say that discussion is ongoing. Like a better, more expressive way to describe those is a work in progress. So.
Thank you. The last question. Okay.
Thanks for your talk. What do you think about the energy-aware scheduler and the work going on around that?
Oh yeah, I was involved in that quite a bit. It's going very slowly, but it's happening. The energy-aware scheduler is, for those of you that have ever worked on big little chips from ARM, you have a CPU cluster, which is like a big power-hungry but very fast CPUs, and you have a smaller CPU cluster, which is going to be smaller, more power-efficient, but not as performant CPUs. And this is a big problem because the whole way the Linux kernel scheduler works, it assumes an SMP system where all the CPUs basically have the same capabilities. And now you have this heterogeneous design. So the point of the energy-aware scheduler is to teach the scheduler how to schedule tasks on the correct CPU to maximize energy savings or to maximize the performance of the use case. If you don't make these changes, then the Linux kernel scheduler will just randomly assign stuff and it won't really understand that this is a fast CPU, this is a slow CPU. So I would say that the most of the work around energy-aware scheduling has been almost entirely in the scheduler, trying to get the task placement algorithms done correctly. As far as the actual power management aspects of it go, dealing with the hardware, that stuff's trivial, I think, compared to trying to teach the scheduler how to be power aware. So, and all of the scheduler maintainers are, of course, very, very throughput and very performance focused, right? They don't want you to introduce any code that may, impact the scheduler. It's a very hot path in the kernel. So that's been a nice education for those of us that have been working in power for years, having to also become very sensitive to that hot path stuff. So.
Thank you very much once again. And
thank you for attending. Thanks.
Thank you.